Yes, welcome back. Let's try continue. I made my English video about these two old computers with my personal computer history museum Denmark is uploading, and actually I need to go on with my project with my washing my underwears, t-shirt and my bathtub. But we can wait 20 minutes. I have to take the water out and put some fresh water 2 times. Then I have do like this 2 times. Then we have to put it. It have to drying many days. I have to put it up there. Try to get the water out. Then put it up there, but this is broken. It's broken many places, broken there, and it's broken on one of the legs is broken. Because I took some bed sheets like this, some heavy wet bed sheets, then it was too heavy. Yes, but let's try to continue a little bit more. Like 20 minutes, and I not understand much of this because I don't have a university degree in computer science or computer engineering. I have an old high school degree, but I like to try read it anyway. I have to read this many times if I should understand, but I have so much else I like to read. So probably I will not read this again because this is too complicated. I not understand. I don't understand this. Yes, but I like to read it. I like to read about this.
During the mid-1980s, beginning with the 256-bit generation. This architecture is favored in modern DRAM ICs for its superior noise immunity. This architecture is referred to as folded because it takes its basis from the open array architecture from the perspective of the circuit schematic. The folded array architecture appears to remove DRAM cells in alternate pairs, because 2 DRAM cells share a single byte line contact from a column, then move the DRAM cells from an adjacent column into the voids. The location where the byte line twists occupies additional area. To minimize area overhead, engineers select the simplest and most area minimal twisting scheme that is able to reduce noise under the specified limit. As process technology improves toward use minimum feature sizes, the signal-to-noise problem worsens, since coupling between adjacent metal wires is inversely proportional to their pitch. The array folding and byte line twisting schemes that are used must increase in complexity in order to maintain sufficient noise reduction. Schemes that have desirable noise immunity characteristics for a minimal impact in area is the topic of current research. Kenner, p. 37. Future array architectures. Advances in process technology could result in open byte line array architectures being favored if it is able to offer better long-term area efficiencies, since folded array architectures require increasingly complex folding schemes to match any advance in process technology. The relationship between process technology, array architecture, and area efficiency is an active area of research. Row and column redundancy. The first DRAM integrated circuits did not have any redundancy. An integrated circuit with a defective DRAM cell would be discarded. Beginning with the 64-bit generation, DRAM arrays have included spare rows and columns to improve yields. Spare rows and columns provide tolerance of minor fabrication defects which have caused a small number of rows or columns to be inoperable. The defective rows and columns are physically disconnected from the rest of the array by triggering a programmable fuse or by cutting the wire by a laser. The spare rows or columns are substituted in by remapping logic in the row and column decoders. Jacob. pp. 358-361. Error detection and correction. Electrical or magnetic interference inside a computer system can cause a single bit of DRAM to spontaneously flip to the opposite state. The majority of one-off, soft, errors in DRAM chips occur as a result of background radiation, chiefly neutrons from cosmic ray secondaries, which may change the contents of one or more memory cells or interfere with the circuitry used to read/write them. The problem can be mitigated by using redundant memory bits and additional circuitry that use these bits to detect and correct soft errors. In most cases, the detection and correction are performed by the memory controller. Sometimes, their CAID logic is transparently implemented within DRAM chips or modules, enabling the ECC memory functionality for otherwise ECC incapable systems. 38. The extra memory bits are used to record parity and to enable missing data to be reconstructed by error-correcting code, ECC. Parity allows the detection of all single-bit errors, actually, any odd number of wrong bits. The most common error-correcting code, a sected Hamming code, allows a single-bit error to be corrected and, in the usual configuration, with an extra parity bit, double-bit errors to be detected. 39. Recent studies give widely varying error rates with over 7 orders of magnitude difference, ranging from 10-10-10-17 error/bit times h, roughly 1 bit error, per hour, per gigabyte of memory to 1 bit error, per century, per gigabyte of memory. 40, 41, 42. The Schroeder et al. 2009 study reported a 32% chance that a given computer in their study would suffer from at least one correctable error per year, and provided evidence that most such errors are intermittent hard rather than soft errors. 43. A 2010 study at the University of Rochester also gave evidence that a substantial fraction of memory errors are intermittent hard errors. 44. Large-scale studies on non-ECC main memory in PCs and laptops suggest that undetected memory errors account for a substantial number of system failures. The study reported a 1 in 1,700 chance per 1.5% of memory tested, extrapolating to an approximately 26% chance for total memory, that a computer would have a memory error every 8 months. 45. Security. Data remainance. Although dynamic memory is only specified and guaranteed to retain its contents when supplied with power and refreshed every short period of time, often 64 ms, the memory cell capacitors often retain their values for significantly longer time, particularly at low temperatures. 46. Under some conditions most of the data in DRAM can be recovered even if it has not been refreshed for several minutes. 47. This property can be used to circumvent security and recover data stored in the main memory that is assumed to be destroyed at power down. The computer could be quickly rebooted, and the contents of the main memory read out, or by moving a computer's memory modules, cooling them to prolong data remainance, then transferring them to a different computer to be read out. Such an attack was demonstrated to circumvent popular disk encryption systems, such as the open-source TrueCrypt, Microsoft's BitLocker drive encryption, and Apple's File Vault. 46. This type of attack against a computer is often called a cold boot attack. Memory corruption. Dynamic memory, by definition, requires periodic refresh. Furthermore, reading dynamic memory is a destructive operation requiring a recharge of the storage cells in the RAM that has been read. If these processes are imperfect, a read operation can cause soft errors. In particular, there is a risk that some charge can leak between nearby cells, causing the refresh or read a phone row to cause a disturbance error in an adjacent or even nearby row. The awareness of disturbance errors dates back to the first commercially available DRAM in the early 1970s, the Intel 1103. Despite the mitigation techniques employed by manufacturers, commercial researchers proved in a 2014 analysis that commercially available DDR3 DRAM chips manufactured in 2012 and 2013 are susceptible to disturbance errors. 48. The associated side effect that led to observed bit flips has been dubbed row hammer. Packaging. Memory module. Dynamic RAM ICs are usually packaged in mold epoxy cases, with an internal lead frame for interconnections between the silicon die and the package leads. The original IBM PC design used ICs packaged in dual inline packages, soldered directly to the main board or mounted in sockets. As memory density skyrocketed, the DIP package was no longer practical. For convenience in handling, several dynamic RAM integrated circuits may be mounted on a single memory module, allowing installation of 16-bit, 32-bit or 64-bit wide memory in a single unit, without the requirement for the installer to insert multiple individual integrated circuits. Memory modules may include additional devices for parity checking or error correction. Over the evolution of desktop computers, several standardized types of memory module have been developed. Laptop computers, game consoles, and specialized devices may have their own formats of memory modules, not interchangeable with standard desktop parts for packaging or proprietary reasons. Embedded DRAM that is integrated into an integrated circuit designed in a logic-optimized process, such as an application-specific integrated circuit, microprocessor, or an entire system on a chip, is called embedded DRAM, EDIM. Embedded DRAM requires DRAM cell designs that can be fabricated without preventing the fabrication of fast-switching transistors used in high-performance logic, and modification of the basic logic-optimized process technology to accommodate the process steps required to build DRAM cell structures. Versions. Since the fundamental DRAM cell and array has maintained the same basic structure for many years, the types of DRAM are mainly distinguished by the many different interfaces for communicating with DRAM chips. Asynchronous DRAM. The original DRAM, now known by the retronym asynchronous DRAM, was the first type of DRAM in use. From its origins in the late 1960s, it was commonplace in computing up until around 1997, when it was mostly replaced by synchronous DRAM. In the present day, manufacture of asynchronous RAM is relatively rare. 49. Principles of operation. An asynchronous DRAM chip has power connections, some number of address inputs, typically 12, and a few, typically N or 4, bidirectional data lines. There are 4 active low control signals RAS, the row address strobe. The address inputs are captured on the falling edge of RAS, and select a row to open. The row is held open as long as RAS is low. CAS, the column address strobe. The address inputs are captured on the falling edge of CAS, and select a column from the currently open row to read or write. Write enable. This signal determines whether a given falling edge of CAS is a read, if high, or write, if low. If low, the data inputs are also captured on the falling edge of CAS. OE, output enable. This is an additional signal that controls output to the data I/O pins. The data pins are driven by the DRAM chip if RAS and CAS are low, WE is high, and OE is low. In many applications, OE can permanently connected low, output always enabled, but switching OE can be useful when connecting multiple memory chips in parallel. This interface provides direct control of internal timing. When RAS is driven low, a CAS cycle must not be attempted until the sense amplifiers have sensed the memory state, and RAS must not be returned high until the storage cells have been refreshed. When RAS is driven high, it must be held high long enough for pre-charging to complete. Although the DRAM is asynchronous, the signals are typically generated by a clocked memory controller, which limits the timing to multiples of the controller's clock cycle. RAS only refresh. Classic asynchronous DRAM is refreshed by opening each row in turn. The refresh cycles are distributed across the entire refresh interval in such a way that all rows are refreshed within their child interval. To refresh one row of the memory array using RAS only refresh, ROR, the following steps must occur. 1. The row address of the row to be refreshed must be applied at the address input pins. 2. RAS must switch from high to low. CAS must remain high. 3. At the end of the required amount of time, RAS must return high. This can be done by supplying a row address and pulsing RAS low. It is not necessary to perform any CAS cycles. An external counter is needed to iterate over the row addresses in turn. 50. In some designs, the CPU-handled RAM refresh. Among these, the Zilog Z80 is perhaps the best known example, hosting a row counter in a processor register, R, and including internal timers that would periodically poll the row at R and then increment the value in the register. Refreshes were interleaved with common instructions like memory reads. 51. In other systems, especially home computers, refresh was often handled by the video circuitry, as it often had to read from large areas of memory, and performed refreshes as part of these operations. 52. CAS before RAS refresh. For convenience, the counter was quickly incorporated into the DRAM chips themselves. If the CAS line is driven low for RAS, normally an illegal operation, then the DRAM ignores the address inputs and uses an internal counter to select a row to open. This is known as CAS before RAS, CBR, refresh. This became the standard form of refresh for asynchronous DRAM, and is the only form generally used with SDRAM. Hidden refresh. Given support of CAS before RAS refresh, it is possible to desert RAS while holding CAS low to maintain data output. If RAS is then asserted again, this performs a CBR refresh cycle while the DRAM outputs remain valid. Because data output is not interrupted, this is known as hidden refresh. 53. Page mode DRAM. Page mode DRAM is a minor modification to the first generation DRAM IC interface which improved the performance of reads and writes to a row by avoiding the inefficiency of pre-charging and opening the same row repeatedly to access a different column. In page mode DRAM, after a row was opened by holding RAS low, the row could be kept open, and multiple reads or writes could be performed to any of the columns in the row. Each column access was initiated by asserting CAS and presenting a column address. For reads, after a delay, TCAC, valid data would appear on the data out pins, which were held at high Z before the appearance of valid data. For writes, the write enable signal and write data would be presented along with the column address. 54. Page mode DRAM was later improved with a small modification which further reduced latency. DRAMs with this improvement were called fast page mode DRAMs, FPM DRAMs. In page mode DRAM, CAS was asserted before the column address was supplied. In FPM DRAM, the column address could be supplied while CAS was still deserted. The column address propagated through the column address data path, but did not output data on the data pins until CAS was asserted. Prior to CAS being asserted, the data out pins were held at high Z. FPM DRAM reduced TCAC latency. 55. Fast page mode DRAM was introduced in 1986 and was used with Intel 80486. Static column is a variant of fast page mode in which the column address does not need to be stored in, but rather, the address inputs may be changed with CAS held low, and the data output will be updated accordingly a few nanoseconds later. 55. Nibble mode is another variant in which 4 sequential locations within the row can be accessed with 4 consecutive pulses of CAS. The difference from normal page mode is that the address inputs are not used for the 2nd through 4th CAS edges. They are generated internally starting with the address supplied for the first CAS edge. 55 extended.
Yes, need to take another break because it's more than 5 p.m. and I have to try to cleaning my underwear and t-shirts. I was out of underwear and t-shirt because I lost more than 30 kilos of weight. So many of my underwears are getting too big. They are getting too big in this rubber bands. So, but I'll do that in Dennis' video. So I will charge the camcorder a bit more, then I will continue. When I'm finished do this, so I will start upload this. So I not understand much of this because I don't have a university degree in computer science or computer engineering, but I like to read about it, and I was looking forward to read about all the different kind of computer memories. So I will continue do that.